different types of differential equations might require different techniques, and some of them we might not be able to solve at all using analytic techniques. We'd have to resort to numeric techniques to estimate the solutions. But let's go to what I would argue as the simplest form of differential equations to solve, and that's what's called a separable differential equation. And we will see in a second why it is called a separable differential equation. So let's say that we have the derivative of y with respect to x is equal to negative x over y e to the x squared. So we have this differential equation, and we want to find the particular solution that goes to the point 0, 1. I encourage you to pause this, and I'll give you a hint. If you can, on one side of this equation through algebra, separate out the y's and the dy's, and on the other side, have all the x's and dx's, and then integrate, perhaps you can find the particular solution to this differential equation that contains this point. Now, if you can't do it, don't worry, because we're about to work through it. So like I said, let's use a little bit of algebra here. To get all the y's and dy's on one side, and all the x's and dx's on the other side, well, I can just multiply both sides times y. That is the effect of putting the y's on the left-hand side. And then I can multiply both sides times dx. That has the effect of putting the x's on the right-hand side. You can treat these differentials as you would treat a variable, when you're manipulating it to essentially separate the variables. And so this will cancel with that, and we are left with y dy is equal to the negative x e to the negative x squared dx. Now, why is this interesting? Because we could integrate both sides now. And so that's why this is called a separable differential equation, and it's usually the first technique that you should try. As I said, this is not going to be true of many, if not most, differential equations. But now that we did this, we can integrate both sides. So let's do that. Now, if you integrate the left-hand side, what do you get? You get, and remember we're integrating with respect to y here, so this is going to be y squared over 2, and we could put some constant there. I'll call that constant plus c1. And that's going to be equal to the right-hand side. And on the right-hand side, we're integrating with respect to x. And let's see, you could do u substitution here, or you could recognize that the derivative of negative x squared is going to be negative 2x. So if that was a 2 there, and if you don't want to change the value of the integral, you can put a 1/2 right over there. And so now you could either do u substitution explicitly or just do it in your head, where you say u is equal to negative x squared, and then your du will be negative 2x dx. So I have something and its derivative, so I can really just integrate with respect to that u. So this is going to be 1/2 with the antiderivative e to the negative x squared, and then of course I might have some other constant. I'll just call that c2. And you might want to review integration techniques for this, as they are needed for separation of variables. Now, what can I do here? Well, I have a constant on the left-hand side. It's an arbitrary constant. We don't know what it is. I haven't used the initial condition yet, so if I just subtract c1 from both sides, the c1s will cancel out, and I'll have a c2 minus c1 on the other side. These are both arbitrary constants, and we don't know what they are yet. And so we can just rewrite this as, on the left-hand side, a y squared over 2 is equal to, on the right-hand side, 1/2 e to the negative x squared. And I'll just say that c2 minus c1 is equal to c. So if you just take the sum of c1 and c2, that is c. And so now this is a kind of general solution. We don't know what this constant is, and we haven't explicitly solved for y yet, but in this form, we can now find a particular solution using this initial condition. So it tells us when x is 0, y needs to be equal to 1. So we would have 1 squared, which is just 1, over 2 is equal to 1/2 e to the negative 0 squared. Well, that's just going to be 1. This is going to be 1/2 plus c. And just like that, we're able to figure out if you subtract 1/2 from both sides, c is equal to 0. So the relationship between y and x that goes to this point, we could just set c as equal to 0. And so we're left with y squared over 2 is equal to e to the negative x squared over 2. Now we can multiply both sides by 2, and we're going to get y squared is equal to e to the negative x squared. Now we can take the square root of both sides, so y could be equal to the plus or minus square root of e to the negative x squared. But they gave us an initial condition where y is positive. So since we're finding the particular solution that goes through this point, that means y is going to be the positive square root. If this was a point 0, -1 on the other hand, then we would say y is a negative square root. But we know in this case that y is a positive square root, so we can get rid of the negative since we're only going to be dealing with the positive square root. So now we could write y is equal to e to the negative x squared to the 1/2 power. And that, of course, is equal to e to the negative x squared over 2. So y equals e to the negative x squared over 2 is a particular solution that satisfies the initial conditions to this original differential equation. Just like that. As a review, because this differential equation was set up in a way, or because we could algebraically separate the y dy's from the x's dx's, we're able to just separate them out algebraically, and then integrate both sides, and use the information given in the initial condition to find the particular solution.